Hello, are you able to hear me?
Yeah, but you're not that audible actually.
Okay, is it better now?
Yeah, slightly.
Okay, how about now?
Yeah, it's better.
Okay. Just give me a second, I'll start sharing my screen. Okay. All right, just give me 1 minute and then we'll start. So, yeah, so just before we formally start, how many of you are planning to come down for the event this Friday, Saturday, Sunday? Okay, see two hands being raised. Okay, so I hope to meet some of you there. All right, so another question. So how many of you have watched the lectures for week 3?
Yes, sir, I have watched three videos.
Okay, what about others? So some 4 of you have raised your hands.
So it's a bit hard to go through the sessions of Machine Learning Foundation Monday because we would have finished the rest of it by yesterday, and today we have to finish it. So we are
Correct,
having a
yeah.
trouble with the Machine Learning Foundation to finish before a live session actually.
Correct, yeah. So that's why I asked. So that just to know how many are there. So I am guessing some roughly 5 to 6 of you have watched and rest haven't. Okay, so that's what I'm planning to do. So it'll be more like a lecture today. But I won't be going over the videos in exactly the same manner. There'll be a slightly different twist to it. It will be presented in a different way. Okay, so that is the plan. And towards the end, if we have time, we can discuss the activity questions. But more or less, it will be like a lecture. So you can interrupt me when you want, right? If you're not able to catch something, and then we can go over that. I hope the plan is clear.
Thank you, sir. We are also dreaming that only.
Okay, yeah. All right, so we'll get started. And see, the first thing is this is the course outline. I know we are already in week 3, but this is just to give you an idea of what the entire course is about. So first week we started off with intro to ML, right? So week 2 was more or less a recap of calculus for ML. And then we went on, then what we'll do from weeks 3 to 6 is we'll be looking at linear algebra for machine learning. So the emphasis will be on ML. At least we'll try to make sure that the emphasis is on ML. 7 to 9 will be optimization again for machine learning. And then 10 to 12 will be probability and statistics. So 10 to 12 will be more or less similar to what you have done in stats 2. 3 to 6 will be similar or will have some components of max 2. And 7 to 9 will be hopefully totally new. Okay, so this is the course outline. as far as today's session is concerned, this will be the things that we'll be doing. So first thing is, why should we study linear algebra for ML? We'll address that first, and then we'll go to a regression problem. I hope all of you are by now familiar with what regression is and what classification is. Okay, so we look at our data set and try to understand what this regression problem is all about. We look at one solution to this regression problem, which is linear regression. Okay, so the rest of the lecture or session will be about trying to understand what linear regression is. Okay, so we'll understand it from two perspectives. One is algebra and the other one is geometry. Okay, so the algebra part will come first, and there first two things will be familiar to you: how to solve a system of linear equations. We'll see why it arises in the first place, and the third part may not be very familiar. Okay, so that is where linear regression actually kicks in. And finally, we will try to understand the whole thing from a geometric perspective. What does it all mean? How does it look? Right? What are we really doing, and so on. Okay, I hope the session outline is clear. As I said, you can stop me in between if something is not clear to you. We'll go over that part. Okay, so first up, why study linear algebra for ML? Right? Why should we study? What's the whole point? So can someone who has gone through the course till week 2, can you tell me why we should do this? Why we should be doing this? Any ideas? Anyone?
I mean, matrix and all are very efficient while doing repetitive and longer computations. Maybe that's why, like, since this majorly will involve such kind of things, maybe while solving multiple equations or approximating a solution for them, it's easy to work around matrix. So
okay, it's a good point. Okay, anyone else?
Yeah, well, like while solving the real life business problems and all, there will be multiple dimensions, multiple attributes which can be actually converted into linear equations and solved. Yeah.
Right.
Yeah, sir. When we're dealing with real data, this basics.
Right. Okay. So I think most of you are there. So a single word answer, I would say, is data, right? So we study linear algebra for machine learning primarily because of data, right? So what do I mean by that? So let's take a concrete example. So assume that there is a housing data set. Okay. So a data set is just a collection of observations, right? So each observation, we call each observation a data point, will be described by these features. Okay, latitude. So each house will have some latitude and longitude, right? So, and it'll have some age, right? So the house might be 3 years old, or it might be 7 years old, and it would have certain number of rooms, and you'll have some area in square feet, say 1,000 square feet, 1,200 square feet, and it'll be at some distance from the school. What I mean by this is, say a school, the nearest school from this house is 3 kilometers. Okay, so these are all descriptions of one house. Okay, and the house also has a price. Okay, a selling price. Let's say you have been living in a house, a 2-bedroom house that is 3 years old, situated at this latitude and longitude, that has 1,000 area square feet, or an area of 1,000 square feet. It is at 3 kilometers from the nearest school. Okay, and this house has a selling price of 40 lakhs, let's say. Okay, so this is data, right? Typical data that you gather from, say, the real estate industry. This is nothing but a vector. So if I strip this data of all these, English words associated with it, and just look at these numbers, what is this? This is just a vector. Okay, so the thing that you have to keep at the back of your mind throughout the course, at least the linear algebra part, is whenever you deal with vectors, somewhere you are talking about some data point in some data set. Okay, so this vector represents one house. So what if we have 100 houses? What do you think that will correspond to?
9 into 100.
Okay, what is that?
Matrix.
Okay, so that's a matrix, right? So if you have 100 houses, then what you can do is, say we had a vector here, right? I'll just make this one row of a matrix 12.9, 80.23, 2003, right? So I'll make this one row of a matrix, and if there are 100 houses, there will be 100 rows. So 100 by 6 matrix, that would be my data, right? So the entire data set, I have represented my entire data set as a single matrix. Okay, so matrices and vectors are nothing but data, right? So it's a choice that you make to represent data in this form, and naturally linear algebra comes in, right? So you have to study linear algebra because you are finally, what is data science? You are manipulating data, right? So this is why we have to study data science, linear algebra in data science. Okay, so that is the basic pitch. All right, so once that is clear, we'll go to the next part, which is regression. Okay, so this is a typical machine learning problem. This is the first problem that is studied in any course in machine learning, which is regression. Okay, so regression is what? You are given some features. Again, I'm given some features of a house, and I need to predict something. I need to predict some real number, which is the selling price of the house. Okay, this is a regression problem. So mathematically, what is it? You are given a data point that is residing in some 6-dimensional space. Okay, this is just a collection of 6 numbers, if you think about it. So this is going to be in some space which I call R6, right? And you need to predict Y, which is the selling price, and that prediction will always be a real number, and that is the defining feature of regression. Given a feature vector, this is called a feature vector. Okay, predict the selling price or some label or target. So I call Y that label or target. So notice that the 6 suddenly changed to n because your features could be n in number, right? It need not be 6. It could be some set of n features, and you have to predict Y. So as I said before, X is the feature vector and Y is the label. Okay, so this is the regression problem which we'll be studying all through week 3. Okay, so that is the problem. So how do we solve this problem? You solve this problem by building a model. So can someone tell me what is a model by looking at this, whatever information you have so far? Sorry, Shumit, I was not able to hear you properly.
The input vector is n dimension, and I'm taking that as the input and predict a single value, which is in our real life.
Yes, right. So yeah, so a model is something which takes a feature vector and pushes that to some label. Okay, so mathematically it's f of x equal to y. So any questions at this point? Okay, so that's a model, right? So this is a model. Okay, so Srinivas, you have any questions at this stage?
Is the y called a label, or since it is a real number, can we name it something else?
Yeah. So we could call it target. So typically
label would be binary, I feel.
Yeah. So see, typically we use label for classification problems where it is either binary or it's a discrete value. But yeah, so if that is a bit confusing, we could use the name target, right? So you have a feature vector, you map feature vectors to targets, right? So it's a real number. So the point to note is that the target or label has to be a real number. Okay, so that is the regression model. So, but the whole point of machine learning is how do you learn this model in the first place? Okay, so there is no machine learning if there is no learning happening. So how do we do that? This is where a labeled data set comes in. Okay, so recall the feature matrix or the data matrix that we had earlier. It was 100 by 6, right? Now what we'll do is we'll generalize it and we'll say that it is m by n, where there are m houses, and for each house you have n features to describe that particular house. So you have m by n values, they will be the features, and therefore the feature matrix or the data matrix. Corresponding to each house, you have a label or a target. There are m such targets for m houses. Okay, and you put them in a label vector. Okay, so this is your setting. This is your label data set. And using this label data set, you have to learn a model. Okay, is this clear so far? Any questions? Okay, so if there are no questions, we'll move on. So linear regression is a particular model, right? It's a type of a model, okay, for solving the regression problem. And here is a simple example. So you have the selling price, which is what you have to predict, right? So this is the quantity that you have to predict, and assume that it varies linearly with the features. So I have here represented only two features. One is the area of the house in square feet, okay, and distance from the nearest school. So can someone interpret this for me? Like, what is happening here? If I give you this equation, what inference can you draw from this?
Only two features are determining the entire target.
Okay, that is one inference. Anything else that we can comment on this?
Hello,
Area
sir.
is increased, then the selling price is going up.
Sir, selling
Then
price decreases by
distance
distance.
is increased, then my selling price is going down.
Okay, second inference is that if area goes up, selling price goes up. If distance goes up, yeah, selling price goes down. Okay, that's the second inference.
Yes.
Anything else?
Everything is happening linearly.
Okay, that is the third inference. Anything else? There is one more point which
Sir, this is a relationship from R2 to R.
Okay, this is from R2 to R. Okay, anything else?
Even though like the house is like tiny and it is at zero distance, there's still some value which is constant, irrespective of it.
Okay, so there is some constant which is always going to be there. Okay, anything else? There's one more point which can be inferred.
So it depends on only two parameters. One is area and distance.
Okay, so Srinivas mentioned that. Anything?
Okay.
Yeah, that's a good point still. But one more point is there which we can.
This 2 and 0.2, it is means this will dictate how correct my selling price I am going to predict, and this will, based on with so many data, we can able to calculate more correct this coefficient term 2 and 0.2.
Okay, so something more related to that 2 and 0.2 I would like to know.
Selling price is more affected by area.
Yeah. So Kamal Kishore, right? Who answered that?
Kamal.
Yeah, Kamal. Okay, so that is what I was looking for, which is that the area is more powerful feature, right here. So
yeah, 10 times more.
Right. So the area is more powerful. Doesn't mean distance is not powerful, but the relative strength of a feature is given by the magnitude of the coefficient, right? So by coefficient, I mean 2 and 0.2, minus 0.2. So the strength of a feature is determined by the value, the magnitude of the coefficient, and its impact on the target, right, is determined by its sign. So how does it vary with the y value? Does the y value go up or does it go down? That depends on the sign. But by how much does it change? That depends on the coefficient. Okay, so a lot of inferences that we drew. I'll just summarize this. So it's from R2 to R. There are only two features. The coefficients determine the importance of the features, right? There is always some constant offset that is going to be there. Okay, so as you can use the data to play around with these coefficients, right? Which is what learning is all about in linear regression. How do I make use of a label data set to choose these parameters, right? I'm using several terms here. If you note, I'm using the term parameter, I'm using the term coefficients. They're all the same, okay? The whole thing will become clear in a while. So what I've done here is just generalize the whole thing, right? Y is the selling price. You could think about area as x1, distance as x2. Theta 1 will be what? 2. Theta 2 will be minus 0.2. And there is no reason why you should only choose two features. You can exploit the entire data set that's given to you and include all the other 4 features also, right? So this is how a typical linear regression model will look like. Okay, so before we move forward, I don't know how many of you have seen the next slide, but is there a way to rewrite this?
Theta transpose X is equals to Y. We can write terms of matrix.
Right. So this is nothing but a dot product, right? So this is a dot product between two vectors. One is the theta vector, and the other one is the x vector, right? So this is just the dot product. Dot product is theta transpose X. I hope you all know that part, right? I think week 2 we already covered this. So okay, since we have already covered this, I will ask this question: why is it theta tan transpose X? Can't I just write theta x?
No, sir, the dot product dimensions will not work that way. Like the matrix multiplication.
Okay, what is the dimension of theta transpose?
So 1/6.
Number of
Cross
parameters.
sir.
Okay, right. So yeah, so more fundamental question: why is theta transpose 1 cross 7?
So theta actually is a column vector, and we are taking its transpose.
Yeah, good point, right? So all vectors in our course and in general are column vectors, right? So that's a convention we are following. That's why theta transpose is 1 cross 7, x is 7 cross 1. Okay, so please remember these things. These are all minor points, but they have the potential to confuse us. Okay, so that is a typical linear regression model. So y f of x equal to theta transpose x. Theta is called a vector of parameters. You could call it you could call it parameters, you could call it weights, you could call them coefficients, but usual terminology is to call them weights or parameters. Okay, so that is what this whole thing is about, right? So this is a linear regression model. Okay, please make a note of it. This should be in the back of your mind all through the rest of this session.
So in the theta transpose matrix, each of the theta is a column vector, right? And the entire thing forms the vector matrix for theta.
So currently we have only vectors, right? So we don't have, we are yet to go to the matrix part. We'll go in a minute, but currently x is small, right? So x is a vector, one house. So think about this as one house. Is it clear? So we are just talking about the model for one house, right? So you take a single feature vector and tell me the selling price of that, predict the selling price of that house. Okay, so matrix will come now. So okay, so keep watching, the matrix will turn up. So y equal to theta transpose x. Now I can also, so what can I write this theta transpose x any differently?
Yeah, you can use the summation also.
Okay, the summation. Anything else that I can do?
Sir, theta dot x.
Okay, theta dot x. Is there any other I can write it?
X transpose theta.
Good. Okay, that's what I was looking for. So all the other answers are also correct, but currently this is the answer I want. So that's why I said this is correct. But anyway, so I can also write it as x transpose theta. So why is this useful? If I write it this way, I can directly jump to the matrix part, right? So notice that this is for one house. X is one house. This is theta. Now, if I stack all these, if I add more column rows to this, right, where each row is one other house, I'll have 100 houses, right? And then this matrix multiplication will give me what? Will give me the predicted selling prices for all the 100 houses. Okay, so this becomes y equal to x times theta, or I've written it as x theta equal to y. So can all of you at this stage confirm that you have understood this? Because if this is not clear, we can't move on.
Sir, one question. I think, yeah, I understand the concept. One question is then, so till now, we have not come up with the means that equation or transfer function for this model, right? Here, whatever the inputs we got, we just created in the matrix format. For example, y1 to y0, y100. It's like for 100 houses, I have collected the price of the houses, and then I put it in the column matrix. That is what Y column is saying about x1 to x6. All these are like parameters, and theta 1, these are coefficients. But at this point of time, we don't have coefficients, right?
Yeah. So yeah, this is a good point. So see, what is happening is, I'll go back to the labeled data set. So there is a slide on labeled data set, right? Where is that? Yeah, see, this you must understand in ML what is given. This is what is given to you. So this X, right? Even though X is usually the unknown, in this case X is the known. Okay, so this is
Correct.
X is given to you, Y is also given to you. Meaning you have, as you said, you have gone and collected the data about 100 houses, and for these 100 houses you have this matrix, you know, this Y, this vector also, you know.
Correct.
Okay, so what you don't know is the theta.
Correct.
So this part you know, this part you know. It is this part you don't know. Is it clear?
Correct. Yes.
Okay. Any other question?
Yeah, understand. Yeah. Thank you, sir. I clearly understand.
Is x theta equal to y? Can you just come back onto that? That x transpose transpose the theta equal to y and x theta equal to y. These two.
See, this part you know, right? Theta transpose x. I'm just rewriting it as x transpose theta.
Yeah.
Okay, this is for one house. So this is, I'll go horizontal and then I'll go vertical. That will give me one y value. So I want to do this for 100 houses, right? Currently I'm doing this for only one house. So what I do is, forget about all these for a moment. This is the same as x transpose theta. I'm just adding more rows here. So I'll do x2 transpose theta, x3 transpose theta, right? x100 transpose theta. I'm just stacking more rows so that this matrix product will give me these selling prices for the 100 houses. Is it clear now?
Yeah.
Can we just label it so that it becomes clear? For the both slides, like 100 data points are there in this slide, and there are 7 features.
Right.
And there are 7 weights in one column vector.
7 weights, correct?
And in one column vector. That is what the initial slide and this slide are there. So if we label that key 100 data points are there, it will be a little more clear.
Right, sure. That we can change. Okay, so this, if I represent it as a single equation, it is x theta equal to y. So I am repeating the call for some feedback. So is everyone clear so far? Or if anyone is not clear, please stop me now itself, because this is a transition point in the session.
I'm clear. Thank you.
Okay. All right. So this is where linear algebra enters. So far, what we have done is yeah.
So just one question. We are not writing this x as x transpose, right? This is the collection of all the data points that we have.
Yeah. This is not x transpose, right? Because this is each row. If you recall the data matrix, each row corresponds to one house. And if you want to do this business for each house, okay, so maybe this x transpose and that x are confusing, but okay, I will just what I will do is, see, there are I need to get a matrix. Okay, so assume that there are only three features, right? So this is your data matrix X. Okay, one area, say 1000 square feet, and distance is 2 kilometers, right? This is one house. Now if I have to write theta, then this theta will appear as a column vector here, right? So I'm not writing that now. I'm just writing the data matrix now. So this one is for the constant, for adding that constant to your equation. Okay, another house, you have 2000 square feet, 3 kilometers from the house, right? So this is your data matrix. Assume that there are only 2 houses. So 2 cross 3 will be your data matrix. And so note that this X is exactly what I'm talking about here. Okay, so instead of 100 cross 7, there what I've shown you is 2 cross 3. Okay, and to multiply that with a feature vector theta. Sorry, weight vector theta. Okay, any confusion now?
Sir, can I ask you one question?
Yeah.
Sir, you are saying that one that other parameters are there. I mean, constant also you have taken, but at the initial stage we will not be knowing about the constants, because in this equation whatever you are showing right now, the theta values are unknown, because those are coefficients which we wanted to find out from this linear regression, right?
Yeah.
But in this X matrix, even constants also we don't know, right? At the start of the project, or maybe when we collect the inputs, that time we don't know what would be the constant for that equation.
Correct. So this theta naught is also a, see this, when I say constant, this theta naught is the constant I'm talking about. Okay, so this 2 into area minus 0.2 distance plus constant, this is theta naught, this is theta 1, this is theta 2.
Correct. Right.
So you don't know, you are right. So we don't know what this constant is. So that is so that is also a parameter. So your parameter, there are 7 parameters for your model. There are 6 features.
6 features.
And but there are 7 parameters, right? So you're right. None of these thetas are known to you. You have to learn. The whole point of the ML setup is you have to learn these weights or parameters. Okay, can I move on now?
Yeah.
Okay. So yeah, so maybe you can revisit this. I'll give you the link. The slides are online. You can access them. So till this part is one section of the session. So now linear algebra enters, right? So now it's all about trying to solve this set of equations. Okay, so this is the setting. X is a data matrix of size m by n. Y is a column vector, right, of size m. Remember, there are m houses. Theta is in Rn, right? There are n parameters. So theta is in Rn. So x theta, that will be in Rn. So is this setting clear? I think this you would have seen in Max 2 itself. So nothing new here. So it's always good to know what vectors and matrices you are dealing with. Okay. So before we go and solve x theta equal to y, what we'll do is we'll solve something simpler, which is x theta equal to 0. Okay. Before moving to x theta equal to y, this is what we'll do. Okay, so I have one small problem here. So if x theta 1 equal to 0, if you are able to find 2 vectors theta 1 and theta 2 such that x theta 1 is 0 and x theta 2 is 0, what can you conclude?
There are infinitely many solutions.
Okay, that is one thing we can conclude. Anything else from a Max 2 perspective?
The x theta 1 and theta 2 equals 0.
Sorry? Shist.
Theta 1 and theta 2 also 0, sir. I mean, the parameters will become 0.
Sir, theta 1 is equal to minus theta 2.
Yeah, remember that x is a matrix, right? Theta 1 is a vector. So we are dealing with vectors and matrices. So, okay,
Sir, x times theta 1 plus theta 2 is also 0.
Good. Yeah. So x times theta 1 plus theta 2 is also 0. Okay. Anything else?
So theta 1 and theta 2 belong to null space.
Yes. Okay. So that is what I was hoping we'll get. So yeah. So both the answers are correct. So if x times theta 1 plus theta 2 is also 0. Okay. And x times some constant times theta 1, that is also 0. Okay. So what can I say? The set of all solutions of x theta equal to 0 is what? What is this?
Linear combination of theta1 and theta2, the null space.
Okay. Is it just the linear combination of theta1 and theta2 alone, or how do you know there are not other vectors which have to be included in the linear combination? Okay, there's just one term I'm looking for. What is that term?
Null space.
Okay, null space of what?
Homogeneous solution.
Okay, null space is correct, but null space of what?
Theta.
X or theta?
Null space of the matrix X.
Okay, good. Okay, so null space of theta doesn't make sense. So it is the null space of the matrix X. Okay, has everyone understood this? Because this is there in the lectures also, but just in case some of you haven't got this, I think you should, if you want, you can go back to Max 2. This is just directly taken from there.
So can you repeat it once?
Okay, which part you didn't understand?
No, I'm just asking for like one linear solution, like moral of all this story.
Okay, so we are trying to solve x theta equal to 0. Now, if you are able to find, say, two solutions, right, then any linear combination of those two solutions is also a solution to x theta equal to 0. Okay, so this means that the set of all solutions to x theta equal to 0, it forms a subspace of Rn, right? So it forms a subspace. This, I hope you remember the definition of a subspace, right? So if you have two vectors and any linear combination of them is there in the original, is a subset of the original space, then this is called a subspace. So I hope you all recollect what subspaces are from Maths 2. Okay, so a particular subspace of a matrix is called the null space. Okay, null space is nothing but all those theta for which x theta equal to 0. That is the null space of x. Okay, is this clear or not?
Yes, sir.
Yes, sir, it's clear.
Okay.
Yes, sir.
All right. So this is the null space.
What is null space?
So the null space is the set of all values theta such that x theta equal to 0. So if you want to express it mathematically, the null space of a matrix X is the set of all theta such that x theta equal to 0. Okay, and this theta should belong to this should be in Rn, right? So this is the null space of a matrix. Basically,
theta belongs to Rn wala part.
So X, okay, see, X is an m by n matrix, right? So X is a m by n matrix, correct? So if X is an m by n matrix, then you're looking at it as, so one way of looking at it is, think about it as a linear transformation. So this corresponds to some linear transformation, right? So that linear transformation is going to send vectors to 0. What all vectors does it send to 0? That will be your null space.
I'm not just getting that statement where what does that value of theta belong to? That statement I'm not clear.
Okay, so theta should be a vector in n-dimensional space, right?
Okay.
For the matrix multiplication to be valid, this is an m by n matrix, so you are multiplying it with an n by 1 vector. So I'm just qualifying this by saying that look for all those thetas in Rn for which x theta equal to 0. So if this statement is not there, then I won't know what to look for, right? Theta could also be another matrix, right, which is compatible with x.
Okay.
So,
and one more doubt is when we are saying we can qualify this and say, yes, there is a linear transformation happening around theta. And again, after the transformation also, all vectors are in linear. That is what we are saying.
What we are saying is there is a linear transformation corresponding to x, which is pushing certain vectors to 0.
It is pushing all vectors to 0.
It is pushing all those vectors which are in null space of x to 0. So that is the null space, right? So x, for example, x can be, let's say 1. Let me take some example. So
suppose, let me just summarize. If x is a set of 100 vectors and null space is a set of 5 vectors, so all the 5 vectors are being made to 0 by this theta. Is that it?
no, right? So see, for example, if x is okay, this won't have any proper null space, but let me take. See, if x is 1 minus 1 0 0, right, and you consider the vector, let's say you take the vector theta equal to, let me take up some vector, something. If I multiply x with this, it should give me 0. Can someone come up with a vector which when multiplied with x will give me a 0? Except 0 0, of course. Minus 1 1. Okay, so if I multiply these two, right, x and theta, so let me just do that.
I think it should be 1 comma 1 theta.
Yeah, you are right.
1 comma 1.
Okay, so this with this, right? So this is what? This is 0 0, right? So this is 0 0. So what I'm saying is that 1 comma 1 vector is in the null space of x, because x into this theta results in 0. So x, this linear transformation x, is pushing some vector to 0. So what? Give me the set of all those vectors which are pushed to 0. That is the null space of the matrix X. Okay, I hope this is clear now. Okay, so any other questions at this stage regarding the null space?
Sir, is it the matrix that pushing the vector
right? So
to 0?
see, once you have this idea of a null space, what you do is you need to find just give me a second. There seems to be some noise. Yeah, so once you have this idea of a null space, you need to do what? You need to find a basis for the null space, right? So can someone tell me why finding the basis for the null space will help?
Then I am able to find all the vectors which can lies in this null space by taking the linear combination of that.
Okay, good. So what is the name for that? Is there a special name for all the linear combinations of that basis?
Spanning set.
Span.
Okay, good. So that is what we are going to do, right? So in case it's not clear, we need to find all solutions to x theta equal to 0. Okay, which is same as saying get me the null space of x. So if I want to get the null space of x, there will be infinite solutions. So I can't go about enumerating one by one. So what I do instead is I say, I'll find the basis for you, and then whatever is the span of the basis, that is the null space that I'm looking for. Okay, so this is what we are going to do now. Now, how do we find this basis? Okay, this is again very familiar to you. We are going to do Gaussian elimination. Okay, so there are 3 row operations. Can someone tell me what these 3 row operations are on a matrix?
Interchanging the rows.
Okay, interchanging the rows.
linear combinations of rows adding subtraction.
Okay, linear combination of rows.
Scalar multiplication.
Okay. So swap two rows, interchanging rows, scaling a row by a non-zero constant, which is the second one, and third one is a scalar multiple of a row to another row, right? You can add this. Okay, so this is something that we all know. So let's take an example. You have a matrix X. Okay, so you want to do Gaussian elimination for this particular matrix. Okay, so what is the, can someone tell me what will be the first step I will do? There could be many steps, but how do I
write the augmented
We will-
matrix?
Yeah, augmented matrix.
We try to make that 2 will be 0. 2 should be 0.
Okay, so see the augmented, yeah, I get your point, but the augmented matrix here is, it'll be a set of zeros, right? So it doesn't make much of a difference if we add or don't add here. Yeah, but so I'll go with this, making the
Making
two.
this 2 and 3 0, sir. Yeah.
Okay, so how do you, can you tell me some operation by which I can make the 2 0?
R2 minus 2R1.
R2 minus 2R1.
Minus
Okay, so we have done that, R2 minus 2R1. Okay, now from here, what shall we do?
We have to make 3 as 0.
R3 minus 3R1.
Okay, that is also done. How to proceed from now?
R3 minus
Third
R2.
row.
R3 minus
R3 minus R2.
R3 minus R2.
Okay. Okay, can we do anything more?
It's done now. All zeros will be.
Okay, it's done. Okay, so again, so I'm going to ask you some other questions. So what is the rank of this matrix?
2.
2.
Wait, 2?
2.
Okay, why is it 2?
Leading
non-zero
coefficient.
Because there
Non-zero
are two
rows.
non-zero rows.
Okay, so there are 2 non-zero rows. So the rank is 2. What is the, so what will be the dimension of the null space of this matrix?
1.
only.
No. Dimension of the null space.
Null space.
Null space dimension is 0.
1, sir. I think.
1 only.
1.
2, sir.
2.
2, sir.
Cross 1.
Okay, I got 0,
2,
1,
sir.
2.
2. Because
Two,
the
sir,
rank
2.
of the matrix is 2 and it was coming from
right,
R4.
2.
So it's
2.
4 minus 2.
Okay, so why, from where did you get this particular information?
Rank nullity theorem.
Okay, can you state the rank nullity theorem?
Rank of null space plus rank of matrix equal to rank of initial domain.
Okay, I'll just write it down. So rank nullity theorem. Okay, so let's consider M by N matrix. Okay, now, okay, so rank of A, okay, plus nullity of A will be what in this case?
And
Number of columns.
Will be N, the number of columns. Okay, so I hope you all remember this because this is kind of needed in this case. So here in our case we have rank 2, the dimension of the domain, the number of columns you have is 4, so the nullity will be 2, rank is 2. Okay, so yeah, so this is the row echelon form of this original matrix that we have been looking at. So do you so I what terminology did you use in max 2 this for the leading coefficients?
Pivots.
Pivot.
Okay, so yeah, so
So
these are,
just one question, sir.
yeah,
The nullity of 2 means there means in the null space there will be plane.
null space will be, yes, plane, yeah, some, yeah, 2-dimensional space basically. No, I mean, so plane in the sense, okay, good point. So it's not a plane, it's a 2-dimensional space in R4. You
It's
get
a
my point?
hyperplane in R4. Right?
Not
No, but
exact.
But
Yeah.
two-dimensional means we understand that is a plane, but anything other than plane that in two-dimensional can, I am not able to visualize it.
Okay. Yeah. So I think it's your, yeah. Don't worry. I would say don't worry too much about visualization, but you are right. So it is a two-dimensional subspace in four-dimensional space. That is clear to you, right?
Yes. Where
Yeah.
my all null space means all solution in null space is there.
Yeah, that is your null space is, yeah, that two-dimensional
Yeah.
space. Yeah, you can assume it's a plane. You are right. Yeah.
Okay.
Right. So yeah, you are right.
But just one question, sir. Miss, this null space means, say, suppose there is a line, that line has to pass through zero. Null space means.
Right.
Because now plane means all plane passing through that zero, right?
Right. Right.
But when I try to visualize, suppose in some case the nullity is 3. That means my null space is sum of 3 dimension which contain that 0 inside it. Is it like that? Or the coordinate means 0 point is on the edge of any of this means that cuboid or paralleloid, whatever.
Yeah. Yeah.
Its location of 0 in case of nullity is 3, where it should be.
0 should be a part of the null space. I mean, the 0 should be there on that surface of the null space. If it is a cuboid or not cuboid, if it is a plane or some, I don't know what's a three-dimensional object, but embedded in four-dimensional space or something. But it becomes tough to visualize. But your point is that 0 should be there on the null space, which is correct. Right.
Means
so 0.
It is in the surface or inside.
Oh, that is okay. That is very tough. Show me. That is very tough to visualize. Because
Right.
it's
No, because why I am asking this, because in one lecture in tutorial, the first tutorial, there is a plane where this RM and Rn concept is given, row space and this thing, and means the picture they mark, they don't intercept with each other, just touching one point.
okay.
So that is why I get confused a little.
Okay, this origin fellow should be there on, it should be in the null space, but whether it is on the surface, whether it is inside, it's a bit tough to visualize. Right. So I would say don't worry too much about visualizing anything which is beyond 3 dimensions. It's very tough.
So essentially in this transformation, the out of the 4 basis vectors in R4, 2 of them have become dependent, right? They're squished onto the other. So the entire R4 space has come on R2. So the origin should still be, maintain its position, right?
Correct,
however, R4 looks, even if we can't visualize, we know that 2 of the basis vectors have come on the other 2 basis vectors.
Right.
They have become dependent. So the origin will not move when these axes is shift, right? When they squish on each other.
Correct.
So it should remain on the same. When it comes on the XY plane, so on the R2 plane, it should remain there.
Right. Yes. Yeah, that is correct. Okay, so see this. These are the pivots, right? So these are the pivots. So the pivots generally, I think they're called they are dependent variables, and in this case, the pivots are not dependent variables. The variables corresponding to the pivots are dependent variables, and theta 3 and theta 4 you are free to vary. Okay, so have you covered how to find the null space in Max 2? Have you covered this part? There is an algorithm to do this. You have done this, I hope.
Because it is part of syllabus.
Okay. Right. So now what we do is, there's a very simple algorithm. You start with so first of all, how do we find all solutions, right? So remember, we are trying to find the basis of the null space. So you initialize an empty set. Okay, and this is the algorithm for each independent variable theta I. So in this case, theta 3 and theta 4 are our independent variables, which you can vary how much ever you want. Okay. So for each independent variable, let's take theta 3 first. You set theta 3 to 1 and every other independent variable to 0. So in this case, I'll set theta 3 to 1 and theta 4 to 0. Okay. And then you solve for theta 1 and theta 2. Once you solve for theta 1 and theta 2, you will get one vector. Add that vector to B. You repeat the whole process for theta 4. Okay, so if you repeat the whole process, you will get another vector. That is this. This is your basis for the null space. Okay, so is this clear or is this not clear?
Yes.
Okay, so
no, not that clear. If you can just spend another 2 minutes on this, in that basis and null space, that relation.
This part, should I start from here? Yeah,
Yes,
so yeah. See, what is happening is the null space has dimension 2, right? So you are essentially trying to find two linearly independent vectors for the null space. Okay, so if you are able to find those two linearly independent vectors, then by definition that has to span the null space. Okay, because null space is two-dimensional. Okay, so according to this algorithm, for now, please treat it as an algorithm. If you want a proper proof, then we'll have to delve into more details. The algorithm states this. You have two independent variables here, two dependent variables. So you have freedom to choose your independent variables. So you set theta 3 to 1 first. Okay, so maybe if you want, we can work this out. So very quickly, I'll work it out for just one case. 1 0 minus 1 0. Okay, 2 minus 1 0 0 1 2 1. 0 1 2 1.
Now all 0.
Zeros. Okay, so I'm going to have theta 1 as it is, because that is what I want to find. Theta 1. Theta 2 also I'm going to keep it as it is. And according to the algorithm, I'm going to set one of the independent variables as 1. I'm going to set theta 3 as 1 and theta 4 as 0. Okay, so if I solve this, what I'll get is I'll get two equations, right? So theta 1 into 1, this will be minus theta 2, right? So this will be one equation. The other equation will be, can someone tell me what the other equation will be?
Theta 2.
Okay, theta 2.
Sir, it will be theta 1 minus theta 3 for first equation.
Theta 1 minus theta 3. You are right. It won't be, there is no theta 3, so it will be 0, right? It will be theta 1 equal to 0, basically.
Yes, sir. Yes.
Or is it minus 1? Am I missing something?
Minus 1.
Okay, this is correct, right?
Yeah. This is
Yes,
okay.
that's correct.
Okay,
Yes.
now what will be the second equation?
Theta 2 plus 2. That's it, sir.
Okay, theta 2 plus 2 equal to 0. So, finally, what vector do I get?
1 minus 2.
1
minus 2, 1, 0.
1 minus 2, 1, 0. Right? So, this is one basis element that I have obtained. So, 1 minus 2, 1, 0. Okay, for now, treat this as an algorithm. If you don't understand why we are doing this, there is like, we'll have to go into slightly more detailed explanation of why we are doing this. If you want a very quick explanation, it's because your null space is two-dimensional. So look at these two vectors. It's 1 here, 0 here, 0 here, 1 here. So this is obviously linearly independent. And since null space of A has 2 as dimension, this has to span the null space. Okay. I know this may not be too clear now, but you can always go back and try to solve it yourself. The algorithm is there.
Just one question. Can we
Yeah.
take something other than 0 and 1 as well, or we should take only 0 and 1?
See, it should not. See, the reason we take 1 and 0 is that forget about the top two components. Just focus on this. I don't want these two to be dependent on each other. So you can take something like 3, 0 and 0, 3. I don't mind, but you should not take something like 1, 1.
Which could be dependent on each other.
Right. Yeah, that's the main thing you have to ensure.
Yeah, thank you, sir.
Okay, so I think that's one part, right? That's the second part, which is trying to solve x theta equal to 0. Okay, so we saw null space entering and then have an algorithm to find the basis of the null space, all that. Okay, so can you just give me 2 minutes, 2 to 3 minutes? I will be back. We will start the next section.
Sure, sir.
Yeah.
Sure.
Okay, sir.
Okay, so shall we resume?
Yes, sir.
Yeah. So remember what we are trying to do. So we are trying to find the parameters of your regression model. Okay. So theta are the parameters of your regression model or weights of your model, and x is given to you, y is given to you. These are the labeled data set. So this is the labeled data set. So you need to find theta basically. So we tried to solve x theta equal to 0 because that's like a simple case before moving on to x theta equal to y. Okay, this is where we are. So now, when will x theta equal to y have a solution? This is the question. So when will it have a solution? Any answers?
When the y is lying on the column space of x.
Okay, so when y lies in the column space of x. All right. So I'm just slightly changing things here. So I'm representing X as n column vectors. Okay, so m by n matrix, remember X is m by n, and I'm using x1 to xn in this case as columns of X. Earlier, if you remember, each X was a row, but it's okay. We are just abusing notation a bit here, but you have n columns of X. These are n parameters, theta 1 to theta n, giving y. Okay, so x theta equal to y. So how do we rewrite this left hand side? Can someone tell me how to rewrite this x x1 to xn into theta? Is there a way to rewrite this?
You can apply set transpose on both sides to rewriting.
Okay, something simpler. So if I were to get rid of matrices, the matrix X, how do I do that? I just want to think about this in terms of vectors.
So theta 1 times the first column plus theta 2 times the second column. That way you can open this.
Yeah, very good. So that is what it is, right? So this is matrix vector multiplication. I can just think about this as a linear combination of the columns of X. Okay, so this is what Shamit mentioned before, that for you to have a solution, Y should be in the column space of X, which is the same as saying that there is some linear combination of the columns which is equal to Y. Okay, only in this case will it have a solution. Okay, so this is the case for x theta equal to y to have a solution. Okay, y should belong to the column space of X. So what next? I don't remember what next. Okay, this is the data matrix, size m by n, m data points, n features. I think this is just to recollect what we are doing. Yeah, so okay, so far we are just looking at matrices, but in the real world, what happens? We look at a typical data set. By look, I mean I would just give you the dimensions so that you can understand it. So let's say you have 10,000 houses. Okay, you have collected the records, you have collected the data for 10,000 houses, right? Let's say there are 10 features. You add few more features. You had 6 to begin with. Maybe you add 4 more. Okay, so yeah. So can 10 vectors span R 10,000?
Difficult, sir.
Okay, is it difficult or is it impossible?
Impossible, sir. Only a subspace they can span at max.
Okay, so what should be the size of, how many vectors do you need to span this space?
10,000.
Rn needs n vectors.
Right, so you need 10,000 vectors. Okay, so why do you think I have asked this question? Why should I ask this question, and why is this question important?
The minimum number of data points required that way?
No, I think to relate
parameter weights. I think we need 10,000 parameter weights. That parameter vector should be in this space, R 10,000.
See, parameters, how many, okay, maybe a more fundamental question. How many parameters are there for this problem, for this data set?
10.
Okay, so there are 10, right? So of course, if you add the constant, there will be 11, but let's say there are 10. Okay, so there are 10 parameters. Okay, but still it's not a question about the parameters. Let me tie this back to what we saw. Can y lie in C of X, right? This is the question we are trying to answer. Can y lie in the column space of X? So for something like this, so probabilistically speaking, right? So if you take, a data set at random which has 10,000 points with 10 features, how possible it is that y will lie in this column space of X? So, okay, maybe I'll rephrase this question. Y lies in which space? Okay, in this case, in this example,
In 10,000 means
R
n equal to
10,000.
R 10,000.
Okay, so y lies in R 10,000. Okay, if 10 vectors can't span, so I need 10,000 vectors to span R 10,000, right? With 10 vectors, what I can span I'll span a very small space, right? So will y lie in the space?
It can, but there is a less chance because it's a subspace.
Right. So there is very little chance that y will lie in the space. Okay, so there's very little chance that y will lie in the column space of x. So I want you all to understand this point, because if this is not clear, then moving forward will be, I mean, you won't understand the link to the next section. So
Can you explain in a different way?
okay, so okay, let's take this example of two features, right? So area and number of rooms. Okay, so area, number of rooms. I'll just keep writing some. So I have now two houses, three houses.
So like calculating null space will be difficult, right, sir? By taking 10,000.
I'm not. Yeah. One second. I'll just come to that. So okay, nine rooms is too much. So okay, so how many houses do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Okay, so this is what? This is 10 cross x is having dimensions 10 cross 2. Correct? So this is x. Okay, so y is, maybe we can write y also. This is x, and I'll write y here itself. Y will be, you can copy this and paste it here. I'm just learning this tool, so it may take some time for me to figure out how to do certain things. Okay. Okay, just leave it. Okay, so assume that I have drawn it this way, and these are the prices in lakhs. Okay, this is some 12 lakhs, 4 lakhs, 5 lakhs, 13 lakhs, 1 lakh. Don't worry about the exact values. It is not my point. Okay, so yeah, so you have 10 houses and the prices for these 10 houses. So your task is really to find, there will be a solution for x theta equal to y if y lies in the column space of x, meaning is there some linear combination of these two vectors, right? First column, second column. These are the two vectors I'm talking about. So is how possible, like how likely is it that this y will lie in the span of these two vectors? This is what I'm trying to ask. Okay, so the argument I'm making is y is in R10, right? Sorry, y is in R10, correct? So y is in R10, and this is a 10-dimensional space. Okay, but the column space of x, what is the column space of x? It is some linear combination of these two columns. Okay, so that is a 2-dimensional space. So I'm trying to, the argument I'm making is, can some vector in R10 lie in just a 2-dimensional space? How likely is it?
Very low. Very low,
right? So that is all I want to impress on you, that it is very tough for this system to have a solution when you have a scenario like this, because you're trying to find some vector in 10-dimensional space and you want it to lie in some two-dimensional subspace of that space. Okay, so x theta equal to y is generally unsolvable in the ML context, right? See, these numbers are not arbitrary, though they are chosen randomly. They are not just chosen arbitrarily, because typically you'll have many data points and you'll have only say 10 features or 20 features, right? So you will have a lot of observations, okay, lot of records, but the number of features describing each record may not be more than say 10 or 20. Okay, under this assumption, x theta equal to y is generally unsolvable. Okay, is that argument clear to all of you?
Yeah.
Okay, so if that is clear.
Features part.
Sorry?
You said ki out of 10 features, a certain lesser number of features are only required. Can you elaborate on that?
Out of 10 features. Sorry, Srinivas, I didn't get the question. Can you?
You just said ki a lesser number of features are more or less, that is what is required rather than the total set of features. You said something similar.
Okay, so what I said was, you will generally find that there are more data points than there are features. So in a typical ML data set, you might have like, let's say 20-30 features for an observation, but you'll have like 10,000 observations, right? So in that case, y lying in the column space of x is unlikely. Okay, so if I had meant a lower number of features, then I'm wrong. So I didn't mean that, but I meant this part, that m is more than n, and in that case it becomes difficult for us to find y in column space of x.
So basically, when you say m and n, so m are rows, right, and n are columns.
Yeah.
Right. So
yes,
m can be more than 10,000 or less than 10,000. That is there.
Yeah, it depends on how many observations you are able to collect, how much data you are able to gather. That how much data you are able to gather will influence m. For each house that you visit, how many observations can you make about that house? That will determine the value of n.
Percentage will be features.
N is n are number of features equal to n.
So basically, it's a field, right? Number of different fields.
Number of different fields in a record, in a table. Yeah, if you are looking at it as a tabular data structure, it is the number of columns, number of fields.
Geometrically, how can we say, how does it possible that R10 is going into R2, is part of an R2 space?
R2 is in R10, right? So R2 means R2 is a subspace of R10. So what we are expecting is some vector in R10 is part of some two-dimensional space.
How can a vector in 10-dimensional space be part of a two-dimensional space?
It can be, right? So for example, if I make all these entries 0, right?
Except, is there any other case except all zeros?
There is, right? So there should be. So for example, see, if you want a two-dimensional subspace of R10, then I could
let us take R4 and maybe bring it down to R2 something. Anything greater than 2, bringing it down to.
Yeah. So let's say you have this kind of a vector. 1, 0, 0, 0. Okay, so this is vector. It's a row vector. So I'm just doing transpose. 0, 1, 0, 0. Transpose. So this span of this, right? So this will be R2, right? I mean, not R2. It's the dimension of A will be 2 of the subspace. So what I'm saying is A is a subspace of.
I'm convinced with the zeros when there are zeros part. And just last point is there a case where there are not zeros and we can do it? Will it be possible?
Yeah. So all that we need is these two should be linearly independent. So we could have, let's say, 1 comma, you just need to find something which is not a multiple. So for example, let's say 1 1 1 1 and I choose 1 1 1 2. I think this should also be. So can someone confirm this is a subspace with dimension 2, right? Because this is not a multiple of the other one, so they are linearly independent, and therefore if you take the span, you will get a 2-dimensional subspace of R4, right, without zeros in any of the components.
Out of a 4 bases, we have only 2 bases. So if we take linear combination, we will get a 2-dimensional. It will be part of the 2-dimensional space, starting from a 4-dimensional space.
Exactly. Yeah. Okay, so that is that. So once this is clear, I think we are moving on to another section now. Okay, this is the most important section. Till this, it's all covered in Max 2. The most important part is what do you do when you are not able to solve x theta equal to y. Okay, if you're not able to solve x theta equal to y, then typically in all engineering disciplines, in all practical sciences, what we do is we go for approximations, right? We try to approximate. We don't give up as engineers and scientists. We always try to approximate. Okay, so the whole point is what is this symbol called? So what does this symbol mean? What does this symbol approximate mean? So can someone tell me with simple examples what we mean by this symbol?
Similar to
Concrete.
Close value.
Okay, I got 3 answers. Similar and another
Equivalent.
one. Yeah, I equivalent. I got one which was close to, right? We'll explore that. What is close to? So do you agree that this is an approximation of 1.234? Is 1 an approximation of 1.234?
Yes.
Okay. Can you give me a better approximation?
1.01.
1.2.
1.2. Okay. Anything better than this?
So whenever we say approximation, up to what percentage we can cover it? So let's say like 3%, 5%, 20%.
Okay, right. That is one way of understanding.
Because here, like you see, 1.23 approximately equals to 1, almost like 23%.
Right. Okay. So you're right. So I'll come to this. So one more round of approximation.
1.1.
1.23.
Okay, 1.1 is good. 1.23 is there. Okay, so if you look at these 3 approximations, which is the best?
1.23.
1.23.
Okay, in what sense is it the best approximation?
It's nearest.
How close to the actual value?
Okay, right. So the idea is that we are slightly now moving into geometry. We are saying things like closest, nearest. Okay, so we are talking about distances. Okay, these are scalars, so we know what this distance means. So this is 0.1, so this is what 0.2, this is 0.02, 0.002, things like that, right? So the distance between the thing you are approximating and the approximation, it keeps coming down, right? So we can all agree that we need to find some distance. Okay, so y is what I am approximating. I call the approximation y hat. So x theta, I'm calling it y hat, and I want them to be close. Okay, so in the space of vectors, what does close mean? It means something like this, right? Distance between the vectors y and y hat. So what will this evaluate to? If I expand the RHS, if I expand this term here, what is it? 2 vectors, distance between 2 vectors.
Yes, sir.
In negative or positive, it will be taken.
Okay, but so have you? I think you have done norm, right? You have done orthogonal. So in Max 2, you have done norms, right? So what is this norm equal to?
Distance between those 2 points.
Okay, distance. But in terms of algebra, now I want to move back to algebra.
Dot product.
0.
Under root of y minus y.
Square of difference in each direction.
Okay, square of distance in each direction. Okay,
Root
so
of square of distance. Yeah.
Okay, good. So root of square of distance. So I want to get rid of the root. So I'm going to do square. So this is sum of squares, right? Sum of distances square. Okay, is that correct?
Yes.
Okay, so this is, so I have my notion of distance here. Okay, so I think some of you might have peeped into the next slide. So I'll just go anyway. So remember, y hat is this. I'm calling it x theta hat. Okay, so y hat, x is a constant here. X and y are constants. So the only variable is theta, right? So that approximation, I call it x theta hat. And what I really want is the best approximation, which is the same as saying minimize this distance between x theta and y and give me that theta which minimizes the distance between the approximation and the true value. And I call the result theta hat. Okay, so is this term clear? Is this operation clear?
No, sir.
Okay, so see, I am trying to find a vector which is close to y, right?
Correct.
So that y hat, what I'm saying is, because I have chosen a linear model, right? I have chosen a linear regression model. That the relationship is linear. So I'm going to say that this y hat is nothing but x into theta hat. Okay. So I want the distance between my x theta hat. Okay, I have missed the theta hat here, but I'm not missed it, but it'll become clear in a while. So x theta minus y, rather the distance between the two vectors x theta and y should be as small as possible. Get me that theta hat for which the distance between x theta and y is small or least.
So basically, here what it does is, for each and every for each and every model, it will calculate the y hat, and then the minimum means I got like y hat 1, y hat 2, y hat 3, y hat 4 using this formula x theta minus y square. Then it will just it will take the minimum value of that y hat. Is that my understanding correct?
It will take the minimum value of the distance between y hat and y. So I will go with what you said. Let's say you consider 5 different y hats. Yeah. So let's say you consider 5 different y hats.
Okay.
Okay. For first one, this distance comes out to be, see, this distance value is a scalar value, right? So finally it's some.
Correct. Exactly.
So let's say first one it comes 1.2, second one it's 0.7. So for the third one, it is the minimum. It is 0.01. Okay. So that particular y hat you take. Okay. And that is what you are looking for. So this y hat is nothing but x into theta. So because of your linear model, you are assuming that y hat is x theta.
So basically we have like 10,000 rows in the data set. So for 10,000 rows, probably it will just calculate y hat for each and every row or every input. And then in the 10,000 y hats, whatever is the minimum y hat, that would be the best model for that given data set.
Again, so you must not look at y hat, right? You must look at the distance between y hat and y.
Yeah, I mean to say distance. Yeah.
Yeah, there is distance between. Yeah. So.
Yeah, correct. I understand.
Right.
Theta hat, I mean to say, exactly.
Right. Okay, so has everyone got this? Because this is like.
Can you draw? I mean, can you draw with some example? Just like.
Okay.
I'm trying to figure out. Yeah.
Okay, so let me first think of how to draw this. So. Let's see. We need to draw what? We need to draw theta. Okay, I have an image that I will be presenting. So
you can make this scatter plot, right, to showcase that.
Yeah. So
close to.
yeah. So I see what I will do is okay, maybe I'll skip a few slides and I will show you the image so that it becomes clear. Okay, so is this so small? Okay, that is as big as it comes. So see, let's say you have only one feature. So that feature is X. Y is your selling price. So you have 1, 2, 3, 4, 5, 7 houses. Okay, so your data matrix will be, can you tell me what the size of your data matrix X will be for this data?
7.8.
10 cross 2.
Okay, the cross 2 I agree, but what is the 7 cross 2,
7
right?
into 2.
Yeah,
7
Okay.
cross 2.
7 cross 2 matrix X. Okay, so you are trying to find and your y is what? Y is some seven dimensional vector. Okay.
Column.
Yeah. So you want to find some theta hat such that x theta hat is close to this 7 dimensional vector. So obviously there's no way you're going to visualize that part. Okay, so there is no way I can show you how to visualize 7 dimensional vectors. So what I will do is I will take you to a simpler case with which is like this, right? So assume that this is your y. Okay, so y is 3, 4. Okay, y is this, x is this. Can you all still see this image or is it too small?
No, sir, we can see.
Okay, see this. I'm zooming out so that you see what x and y are. See, this is, forget about the houses because this won't make sense if you think about them as houses. Now you have to think about just vectors. Okay, so x is some matrix, y is 3, 4. This is 3, 4. This is y. Now you want to find something which is close to y, and x theta hat is this thing, right? It's so this line that I've written, right? So I'm calling this line C of x. So can someone tell me what the C of x is?
Column of x.
Okay, it's the column space of x, right? Because see, the columns are what? 2, 1, 6, 3 is nothing but 3 times 2, 1. So the column space of x is only this line. That line passing through the vector 2, 1. Okay, so where will this x theta hat lie for any whatever theta you think about? Where will x theta lie?
On this line only.
Okay, right. So it has to lie on this line because x theta is nothing but a linear combination of columns. Remember that one equation we had, x theta matrix vector means linear combination of columns. So x theta is going to lie on this line. So what I am really asking for is find for me some vector in this line which is closest to y. Can you think of what that vector will be which is closest to y on this line?
The
Yes, sir. We're
perpendicular
trying up
projection.
or down to, and means taking 4 from up.
Right. So the perpendicular, this vector 4, 2, that is the vector which is closest to y, and that will lie in the column space of x. Okay, so this is what we are trying to do now, basically. So if you wanted the picture of what we are approximating, this is what we are approximating. We are trying to find a vector in the column space of x which is as close to y as possible. Okay, so this is called a projection. Okay, we'll come to this, but let's go back. Yeah, so where were we? We were here. So now remember the 2D picture that I showed you. Y is this 3, 4 vector, and x theta is some vector in the column space of x. You are trying to find that x theta which is closest to y. Okay, is this now clear with that picture? I hope this is clearer.
Right. Yeah.
Yes, sir.
Okay.
Much clear.
Yeah. So this theta hat you have to find. Okay. So this is an optimization problem. So we'll explore optimization in week 7 to 9 in much greater depth. But the central piece of many ML algorithms is this thing called loss. So we are trying to minimize this, right? We are trying to minimize the distance. Usually this quantity is called the loss. Okay, there is another way to understand the loss. So this is a more practical way of understanding the loss. So for example, you have, let's say, I'll go back. So x theta is what? Now come get away from the linear algebra part and think about it from a practical scenario. What is y? What is x theta?
Can I use deviation word instead of loss? I mean, is it equivalent in this case?
Yeah, that is it is a deviation. So it is a deviation of what from what?
Prediction to actual.
Predicted versus actual.
Okay, very good. Right. So y is the actual selling price. Okay, y is a vector, but I think you can visualize it. Y is a vector. So it's a vector of selling prices, right? So if there are 100 houses, then you have 100 selling prices here. X theta is the predicted selling price. Okay, again for these 100 houses. You are trying to minimize, the deviation or the error in the prediction. Okay, you are trying to minimize the deviation or the error in the prediction. That is what we mean by x theta minus y. So I'll just use y hat here so that it becomes clearer. So x theta minus y, norm of this, right? So this is what I was saying. So what I'm going to do is, this is the same as y hat minus y. So 1 squared I'll add. Okay, so y hat is what? The predicted value. So remember, if there are 100 houses, then this will be like 100 values. So y hat 1 minus, I'll just write it as summation so that life becomes simpler. So this will be sum over, okay, how do we add this? Yeah. So house number 1 to house number 100. So this term I call the loss. Okay, so x theta is nothing but y hat, which is the predicted selling prices. Y is the actual selling price. I want to minimize the sum of the squared errors. So you can think about each one of this as an error or a deviation, right? It has to be y actually, but I am only able to predict it as y hat, right? So y hat minus y is the error. I don't want to be bothered by the sign of the error. So I square it and I add all of them together for 100 houses. This is what I call the loss. Okay. So
sir, one silly question, sir.
Yeah,
Why can't we can take y minus y hat?
Yeah, that is also correct. Both are equivalent, right? So when you square it, it will become the
positive value only.
Yeah, it will get consumed by the square. So it can either be y minus y hat or y hat minus y.
Yes, it is the absolute value, right?
It's the square, right? So yeah, I mean, absolute value is what you will get, but since you are squaring, the sign doesn't matter. Whether you do it this way or that way, it doesn't matter.
Yeah.
Okay, so this is the practical interpretation of the loss. Yeah.
So in that formula, why that n equal to 100 it has shown, so it should be n, right?
It should be m. I took
n.
It should be m, right? Because x is m by n, theta is n by 1.
X is r.
Right. So that is okay. So I hope at least one of these two interpretations you got. You can either think about it geometrically as the distance between y and its approximation x theta, or you can think about it practically as the distance between the prediction or the error in prediction and the actual value. Okay, so the whole point is yeah. Yeah, go ahead.
I mean, so here you are explaining loss, and earlier also we have same algorithm, right? Argument minimum of um, x theta minus yeah, this one, yeah, theta hat, yeah, theta hat. Same. This is the same thing what you are talking about. That
Same
loss,
thing,
right?
yeah. So this quantity I call it loss. X theta minus y norm square, I call it the loss.
Okay. Got
Okay.
it, sir.
So the reason I call it a loss is because it in the practical ML standpoint, it is you are losing out on some because of your incorrect prediction. This is what you are losing out on, and therefore it's the loss.
Yep. Quantities. Yeah.
So what does the arg represent for?
Sorry, what does
ARG? In the previous slide, it's written ARG.
Oh, argmin, right? So see, you have seen minimum. Argmin will give you that. So you are minimizing over what? You are minimizing. What is the parameter you are trying to? What is the parameter space is theta, right? So
yeah,
the argument. So in programming terms, this is the argument for a function. So if you write some Python function, that will return this particular value to you. So you can think about this as a Python function which returns this argument over which you are optimizing.
Okay. It's a programming representation.
Not programming representation. I just told it that way, but
compared.
Yeah. So you are minimizing a value. So if I ignore arg, right, I'll get the minimum value of this expression. By adding this arg, I get the value of theta for which this expression is minimized.
Okay, sir. Got it. Got it.
I have a question.
Yeah.
So let's say like we have big data, right? And in the real world, what happens? Like, do you think like this is an ideal condition, or we you know, like if we have big data, so then this loss can be zero also. Let's say like machine learning the algorithm where like we want to minimize the loss. But do you think like in any case, in the real case, like we can minimize this loss as zero?
No, very unlikely. So you are it's a good question. So in a so it can happen, but what will happen is that you will end up memorizing the training data set. So you remember that in week 1 we studied this training, validation, and test.
So I have one. Yeah, I have one more question.
Yeah.
So if it is not, you know, I understand like this is an ideal condition, and in the real scenario, like there would be deviation. So like, you know, like if I compare it with the human mind, right? Because we are trying to adapt human mind with computer, correct? This is what machine learning algorithm is there. We are trying to create the learning thing. And then on top of that, like we are creating the intelligence, right?
Right.
So I mean, like sometimes or in many cases, human minds are biased, right?
Right.
Biasness is based on certain kind of, you know, past experience or whatever data is fed in the mind or brain, right? So similarly, like here, like as we are using big data and based on that, like machine learning algorithm will predict something. So do you think like machine learning algorithm can be biased also?
Yes, yeah. So there have been, in fact, it's a good question. So there have been instances recently with the advent of several ML systems making it to mainstream use cases, right? So there is this whole field emerging called as ethics in AI. So ethics in AI is all about addressing these things. So machines can be extremely biased. For example, you see, it depends on the data, right? So if you're going to, if your data is going to be biased,
we are getting
whatever we're gonna provide that on the basis of that, that's gonna predict.
Correct.
So so see, that is fine. Like data can be in two ways, right? One can be synthesized data. So there, like of course, like we can ask machine to become biased. But I'm talking about the real data. Let's say
real
like
data itself. Yeah. So for example, natural data, right? So for example, you are trying to do something, there might be gender imbalance in your data set. So I don't know in what way, but your original data set itself, it might very poorly represent a particular gender. Okay, so your machine will inherit that bias. Okay, you didn't design it that way. Probably you didn't know that the data you provided to the machine had gender imbalance, but because of the nature of the data, the machine is going to learn a biased model. Okay, so it was not by design. I mean, you didn't say that, you didn't synthesize data and ask the machine to learn it that way, but because the data was biased, your model also became biased.
Yeah. It will totally depends upon the data.
Yeah, so a lot depends on the data. Of course, the model we can only do so much, right? So this whole computer science principle of garbage in, garbage out is still there. So if you give it some very bad very bad representative data of the population, then your model can only do so much.
Yeah.
Okay.
Excuse me, sir.
Yeah.
So there could be one way where we can take the loss to 0, right? If we set m equal to n, as in we drop enough points so that the number of data points is equal to the number of features, then so we can get an exact inverse. Theta will be equal to y times x inverse.
Okay, so even if you get that right, see our aim is actually not to drive the loss to 0. Okay, so our aim is to build a model that is as predictive as possible, right? That so there is a term in ML called generalization, right? So it's a very important term, and I think we should teach you that at some level. So see, you are using some training data set, right, to learn the theta. So the whole point is, how does it perform on a test data set that the model has not seen before? Okay, so even if you drive the training loss to 0, that makes no difference, right? What is important is the final exam day. On exam day, you will be getting a different question paper. So maybe you'll have a different set of houses for which you need to predict the selling price. So that performance is what matters ultimately. Okay, so
if we drop the data points just to get an exact inverse, then we lose some information in that process.
Right. Yeah, you always risk that.
For the zero case, when we say that we said that a probability of R10 landing in R2 is very little karke. We said a vector which is a 10-dimensional vector coming into 2-dimensional is very difficult. It has less probability, was our initial statement.
Right.
But still, there is some probability that it might happen.
True. There is some probability
When
that
that happens, it will go to 0. However unlikely it might be.
True.
That is the only case when this will go to 0, but it is not realistic. It might happen, might not happen. That is a different issue. But a case exists. That is it.
Yeah, a case exists. Yeah.
And it might be hypothetical, might be real, is a secondary issue.
Yeah, but it is possible. Yeah.
And from an R2, luckily somehow R10 came to R2 and everything matched. And somehow we found it also.
Right.
And that argument wala previous slide.
Yes.
In that, it is like simplifying it and saying it is an equation in theta, and we are just finding the minimum of theta. That is simple as that, and rest all are just constant type.
Yeah, we are finding that value of theta for which the expression is minimized.
Generalizing it, simplifying it and saying it is just an equation in theta. Instead of theta, you can say it is an equation in theta, and we just wanted to find that value of theta which is minimum.
Right. Yeah.
And are theta the weights of the equation coming from the initial terminology?
Yeah, it is the same thing. Yeah, it is the weights of your model. That is what theta is. X is the data matrix. Y is the label vector.
And theta are the weights. We call it weights, coefficients, or parameters.
Parameters. Yeah, the same thing. It's the same theta that is coming in here.
Yes, sir. So in that case, when we are going for in the general case, when the m is much larger than n, then there could be a particular case where there is an exact overlap that you get with the y. But if you forcefully set m equal to n, you will always get an inverse. But then we may lose some information. So
yes.
would be the summary, right?
Yeah.
If we forcefully put m equal to n and drop points, then there will always be an inverse. So we will definitely get some y, which is an exact equal, but then we lose info. But if we have more y, then we can't get an exact inverse.
Right.
But is the inverse mandatory?
Yeah. So see, even I'm not sure if you'll be able to get an inverse also. The x has to be invertible, right? Even if you drop some feature in some data points and make it a square matrix, it's still not guaranteed to have an inverse. So that also
it's not guaranteed, but there is if a rectangular we can't get that, but for a square it may be possible.
Maybe possible, yeah. Okay, so
Sir,
we are,
speed up, sir. Geometry part also is left.
yeah. So this, yeah, what we can do is we can now rewrite this loss as x theta minus y transpose x theta minus y, right? So this is just the norm. I'm just rewriting the norm as dot product. Okay, so there is nothing more to it. So why am I doing this? This is the optimization part. Unfortunately, I'll have to skip the mathematical details. So when you want to optimize a function, you find the gradients, right? So you find the gradients, set them to 0. Here you have not just one gradient, you have a vector of gradients, right? I mean, sorry, gradient is a vector, but you have a vector of partial derivatives, right? So you have to differentiate L with respect to each of the thetas. Set them to 0. Now you will end up with this expression. Okay, so if you are looking for where all this came from, you can, there is one section in the appendix, okay, in the book, which talks about, I'm sorry, this is for whatever reason not loading. Okay, I'm looking at a local site. Okay, so I will direct you to that. It will tell you how to differentiate loss with respect to theta. It talks about the chain rule, so there is a big derivation, long derivation. Okay, at the end you will end up with this fellow. Okay, you have to trust me on this, and later on you have to go and look at it. So finally you end up with this expression. If you differentiate the loss with theta and set it to 0, you will end up with this. Okay, so you have, there's no other way but to trust me on this and move on, because if we go into the derivation, it will take all day. Okay, so these are called the normal equations. Okay, this is the, the end of the whole thing. At the end, you have to have this set of equations. So we'll spend a brief while on this. If x transpose x is a matrix, right? So if that is invertible, then my final solution to this whole setup is theta hat equal to x transpose x inverse x transpose y. Okay, I just take the inverse of this and say that this is the argument that we are looking at, right? This is the argument. Okay, so now the question is, when is this invertible? There is a, so you have to, for that you have to study this x transpose x in some detail. For now, I'll skip this because the geometry is more interesting. So I'll come back to this and we'll spend some time on this part. Okay, so what does finally, after doing all this, what is a linear regression model? How does it look like? Okay, so remember we are looking at this data of 7 houses. There is only one feature, x is that feature, and this is the selling price. Okay, so each point here represents one house. So theta transpose x, right? That was our model. Theta transpose x is nothing but theta naught plus theta 1 x in our one feature case. Okay, this is nothing but the equation of a line. So this is why this is called a linear model from the geometry point of view. The model is just a line, and what kind of a line? Can someone tell me what line I'm looking at? So there are so many lines, infinite number of lines that I could draw. Why did I choose this line, or what criterion do I choose to draw this line?
That has a least amount of loss.
Best fit line.
It has a less loss.
Okay, so this has the least loss, right? So this line has the least loss. Loss is what? Actual minus predicted square, and you sum all these errors, right? So remember this, all the red points are the predictions. Okay, all the blue points are the actual selling prices. Red points are the predictions. The distance between them is the error. Square of the distance you add for all the 7 houses, that is the loss. So a linear regression model is that line which best fits the data. Okay, so this is called a best fit line. Okay, so this is what a linear regression model is. If you think about this in higher dimensions, if you go to 2 features, this line will become a plane. Okay, and if you have two features, it will become a plane. And then if you go to some n-dimensional space, it becomes what is called a hyperplane. Okay, so hyperplane, none of us know what it is. We can't visualize. So always stick to two-dimensional and three-dimensional case. So if you're able to understand this, then it very easily extends to n-dimensional case.
So hyperplane basically definition theoretically it is a n-dimensional plane. Is that so?
Okay, so if you want to know what a hyperplane is, I will again direct you to the notes. So in the notes, this very closely follows what we have done here. So same images. I have like mentioned what we mean by a hyperplane. Okay, so this is an equation of a plane for two-dimensional case. So if you extend this to an n-dimensional case, then you get a hyperplane. So basically, a hyperplane is something which has dimension one less than the space in which it is there. It is embedded in. Okay. So for example, this line is in a two-dimensional space, right? This line is in R2, but the line has dimension 1. Okay, so in general, if you look at Rn, then a hyperplane will have dimension n-1. It will have a dimension 1 less than the space in which it is present. So for example, a plane has dimension 2, but it is embedded in R3 or in space. Okay, so I can refer that. Okay, so coming back, there's one more piece of geometry which we just saw, which was what? So if you try to solve this equation, you will get some theta hat, and this x theta hat, right, is an approximation for y. Remember that we were trying to do that. Find that x theta which approximates y. So yeah, so one natural question is, how are these two related geometrically, right? So approximation and original vector, how are they related geometrically? And this is what is the diagram that we saw before, right? So if y is this, then if x is this matrix, then this column space of x is this line. So this is x theta hat, right? This is the nearest vector to y. So this is the vector we are looking for. Okay, so yeah, so I'm just now generalizing this. If you have a y and if you have an x theta hat, then the error vector, right? The error in prediction is what? Y minus x theta hat. So are you all with me on this? This is an important part. Last few minutes of the session. So are you all with me on this?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so the error is actual minus predicted. Okay. Now the error is perpendicular to the column space of x. Notice this. This is the error. It is perpendicular to the column space of x. Okay. That means what? If you look at the columns of x as x1 to xn, then E is perpendicular. The error vector is perpendicular to each of these columns, which means xi transpose E is 0. Is this correct?
Yes.
Okay,
Yes,
xi
sir.
transpose E is 0 for each I. I just rewrite this as a matrix form. If I put all the xi transpose, then I'll get x transpose. So x transpose E is 0. E is what? E is nothing but y minus y hat, y minus x theta hat. If I multiply this, then I get the same equations that you saw before. This is another way of deriving that expression without using the loss. X transpose x theta hat equal to x transpose y. Okay, so is that clear?
Yes, sir.
Okay, so I'll
Sir,
just.
y minus x theta cap is some type of the Tonian error, sir. Loss
This is an
value.
error, right? Y minus x theta hat
Yeah.
is an error.
Oh, okay. Yes.
Okay, so I'll just summarize and I'll go back if there are any questions. So we first started off with linear algebra for machine learning. Why should we study linear algebra? Because of data, right? Data is in the form of vectors and matrices. We took up a regression problem. Regression is nothing but convert feature vector to a single real number. Dataset is some housing dataset that we took up. Each house is described by some features, and we have to predict the selling price. So there are many kinds of regression models. We looked at the simplest model called linear regression model, where you assume that the selling price is related to the features linearly, right? So theta transpose x. So once you express it that way, it gets converted into this equation x theta equal to y. Before solving x theta equal to y, we tried to solve x theta equal to 0, and then we went to x theta equal to y. When we went there, we noticed that it's very difficult to find a solution. So we tried to approximate it, x theta approximately equal to y. In trying to solve it, we had to introduce this notion of distance between two vectors. And we also came across this loss of prediction. The loss is nothing but the distance between the predicted value and the true value, right? So our aim was to minimize the loss. Okay, and then finally we viewed all this from a geometric lens of linear regression, meaning a line that best fits the data points by minimizing the errors, which can also be viewed as projecting y onto the column space of x. Okay, so that's the summary of what we have done so far. Maybe for another 10 minutes, if there are any questions, we can discuss. If not, we can close.
I have a question related to hyperplane.
Yeah.
So see, I mean, up to 3 dimension, we can visualize, right?
Up to 3, it's kind of possible, yeah.
Yeah, and beyond 3, like, it's very difficult to visualize. Or I don't know, like, I cannot visualize. So whenever, somebody thinks about hyperplane, so mathematically, like, it's fine, like they have formulated and put the equation. Then how to imagine it?
How to imagine a hyperplane?
Yeah.
Okay,
because
so
until unless in mathematics, if you don't visualize, right? So it's very difficult for you to, inculcate.
Right. So the trick that many mathematicians do, and which we should also follow, is visualize everything in R2 and blindly trust your instincts that this is how it works in Rn. So for example, see, I made a very loose argument here. The argument I made was the error vector is perpendicular to this line. Okay, this line is the column space of X. But this was only for a particular matrix, right? This matrix here. In this case, the column space happens to be just this line. Okay. And I said error vector is perpendicular to column space of X. Now I generalize this. Right. So this is how we typically do. Think about it in 2D and 3D and trust your algebra to take you to RF. So that's the trick. So I also checked with Subhajit. So Subhajit is, your Max 2, Max 1 instructor, right? So he's a PhD candidate. He's about to complete his PhD in mathematics. So I asked him, how do you do this when it becomes too abstract? What do you do? And something similar he told me, that you always start with things which you can visualize, and then slowly you build on top of that, and you go to very abstract ideas. Okay, any other questions?
Sir, I have one question, sir.
Yeah.
In the lecture, we studied 4 fundamental subspaces.
Correct.
Out of that 4, 2, it's clearly means I find the uses of these 2 subspaces. One is column space and second is null space. Right. But where this left null spaces, I'm not able to visualize that thing, and how and where I use that also is not very clear to me.
I am also not very clear about the other 2, so don't worry about the other 2. If you know null space and column space, that is enough. Right. Honestly, I also don't know where the left null space. See, left null space and the other one, row space, right? They can also be written as null space of A transpose and column space of A transpose, right?
But that is just a mathematical formula.
Correct,
but
yeah.
I'm not able to see that like the way I able to see the column space and null space. Yeah,
so I am also not able to see. I'll let you know, right? If I if I am able to find some concrete uses for it, then I will get back to you. You also do the same, but until then, it remains a mystery.
Okay, so one more question. In the lecture, sir, the tutorial, if you go to the lecture tutorial, sir.
Okay.
Sir, before that,
go
once you
to
share the PPT file,
3.1, sir.
Yeah.
3.1.
Yeah. So PPT, it is there in the slides. If you go to the links, you'll be able to find week 3 link to the link to week 3. Yeah, tutorial
3.1, sir.
Okay.
Or else you can go to this PPT, sir. Don't play the video, sir. Supplement.
The PPT, yeah.
Yeah.
Week
3.
Okay, week 3 tutorial
3.1, sir. Tutorial 1. Yeah.
Okay.
So go down. Yeah. Oh, wait. That figure, sir.
This one, huh?
No, it's up. Next.
Oh, this
before.
one. Yeah.
This one, sir. In this one, I just want to know, sir, this row space and null space. There are two spaces they are marking and connecting with a dot, not overlapping, not inside. I don't understand why this figure like this.
You mean to say this C of A and N of A transpose, there is only one dot here?
Yes, why? Because is there any particular reason to do this?
The reason, right? Because they are orthogonal, right? These two spaces are orthogonal to each other. So
yes, but
then
if you slide, sir, if you null space and this row space, if you fit, means if you just gradually slide this null space block to the row space, that also orthogonal, sir.
Null space 2, yeah, that is C of A. Yeah, they are also, these two are also orthogonal.
But this figure I also saw in the internet. This is like in this way only. Is there any particular reason? They are not doing, they are overlapping, they are only touching this in a point, not in a line even.
You mean to say these two rectangles, right?
Yes.
Yeah, because they cannot have any other vector other than 0 in common, right? If two spaces are, so let's take these two, right? Null space and column space of A transpose. So null space, so we are saying null space of A is perpendicular to column space of A transpose, right? See, you have AX equal to 0 for null space. Okay, so what does this mean? This means, okay, AX equal to 0, then this means X1 transpose. So if X1 and X2 are the rows, okay, just give me I need to write it as a matrix. So X1 transpose is row 1. Okay, so this is what Xn transpose. This is n rows. Okay, there will be m rows, right, for m by n. So this is matrix A, and then I say that some x equal to 0. So this x belongs to null space of A because Ax equal to 0.
Yeah.
Now, what does this mean? This translates to X1 transpose X equal to 0, X2 transpose X equal to 0, so on till Xm transpose X equal to 0. So basically this means what? Xi transpose X equal to 0. So this means what? This is perpendicular. X is perpendicular to Xi transpose, X2 transpose, and so on, which is nothing but X is perpendicular to the column space of A transpose. Are these two statements clear?
Yeah, so that is true, but suppose, sir, in the room, in any room, two wall which is perpendicular to each other. can I say ki this wall is null space and that other wall which is
No,
perpendicular
no.
to?
No, right?
That,
Because
yes,
yeah,
why
see,
that is the
okay, that is the question, right? So let's
Yeah.
say, now let's say that there is some vector which is in, okay, what? Some random symbols are getting printed. Okay. So let's say that X is in null space of A. Okay. Now you are asked, now let's say that X is also in column space of C of A transpose. Okay. You're basically asking if there can be a line of intersection between these two spaces.
Okay.
Okay, if that happens, then you will end up with the equation X transpose X equal to 0, which can only happen if X is 0. Okay, only point which is common to the null space of A and column space of A transpose is this 0 vector.
Right.
Okay. So, but that was a good question. I didn't think about it this way, but yeah, that's a good question.
Okay. There only and only 0 can be there because the dot product, because all the vector perpendicular to this field and that field should has to be 0. Otherwise, it's not a orthogonal, right?
Right.
Got it, sir. Thank you.
Right. So, any other questions? Anyone?
Can we repeat that 1.1 wala part after that?
Sorry.
Where we approximated 1.1.
1.1.
In one of the slides, we approximated something 1.2. After this, whatever is after this.
This part?
Yes, this part.
Yeah. So, see, we are the defining feature of this approximation is that each approximation is getting closer and closer to the true value. Okay, so each approximation is getting closer and closer to the true value. So that is what I want to do for vectors also. Here I am doing this for scalars, where y is a scalar, y hat is also a scalar. What happens if y and y hat are vectors? I need to find the distance between y and y hat and look for that vector y hat which is closest to y, and hence I try to minimize this. Right, so it's the basic idea of distance. Is it clear?
In summarize, we can go to that slide. Second, I'm summarizing it this way: ki we are finding some sort of theta
Right.
where we will, the distance between y hat and y is minimized.
Yeah, right.
But I'm still not sure. But somehow it is something like that: ki we'll find the values of theta because there is no value of theta in which x theta is equal to y. We are just trying to finding out the minimum value of, the difference should be minimum is what is trying to, is that it?
Yeah. The difference between the predicted and true selling price, that difference should be minimized. In terms of vectors, it's the distance between the predicted vector and the true vector should be minimized.
So in this theta, no, backslash theta hat, where theta hat and so here theta hat is the predicted weights. Are these the predicted weights, theta hat?
So there's no concept of predicted weights, right? So you have only weights. X theta hat is the predicted selling price using the weights. So you have only weights.
What is theta hat and theta? What is the difference between
So it's more like a variable, right? So this is a variable. Here I'm using theta as a variable. Theta hat is a realization of the variable. So it's like the result that I get after it's a particular instance of theta, right? So after I do the minimization process, I get this vector of weights that I call theta hat.
Out of a set of all thetas, I have one theta hat,
exactly.
which is the right theta hat as per me.
Yeah. That is the best theta hat according to you. Yeah. You are scanning the space of theta hats and you are scanning the space of theta and then you are picking one theta hat from there.
Again, space or set of theta, we have one theta hat which will give us the minimum of whatever we are trying to do.
Yeah.
Okay, now it's clear.
Okay, so any other questions? If not, we'll close.
Sir,
Yeah.
sir, can you go to the slide where you said there are 10,000 and 10 and it's not possible? The probability is very less.
Yeah.
Sir, what does or how does it translate to the house example that you gave?
So you have 10,000 houses, and then you have, for each house, you collect 10 observations, right? For that house, 10 features for that house. So what you are saying is that, okay, so some point you have to enter mathematics. So I'm saying that you can't find 10 parameters or 10 weights that will accurately predict, right? Accurately in the sense with absolute precision, the selling price, the exact selling price of the house. So I cannot be flawless in my prediction is what I'm saying. I cannot find a set of 10 parameters which will flawlessly give me the exact selling price of these 10,000 houses. That's not possible.
Okay.
Okay, so think about it, right? So you have 10,000 houses, and you are saying that with just 10 numbers, okay, and some observations about the house, down to the last decimal point, I can give you the selling price of each of those 10,000 houses. That seems a bit unlikely, no?
But sir, how does varying n helps? Like, if I increase the parameters, how does it help? Because even though 10,000 is a very big number, so we won't be able to exactly pinpoint each and every one of them, right?
Correct, right? So that's the point. So we can't do that, and that's why we can't solve this exactly. So I am not increasing n, right? So n is fixed. I only have so many features for a house, and I have only these many houses of data for these many houses. 10,000 houses is all that I have information for, and for each house only 10. So these are kind of fixed, right?
Yes, sir.
Yeah. So now can you tell me what the question is? I didn't get it properly, I think.
Sir, my question was no. It got clear. My question was what does m, n, and this the statement can 10 vector span are 1,000 10,000. How does it translate to the house example and the parameters?
Yeah. So can I find 10 parameters that will perfectly describe the relationship between my houses and their selling prices?
Okay, with 100% accuracy.
Yeah, 100%. Yeah, that is what I want. So the loss has not yet come in at this stage, right? So we are not talking about approximate solutions. We are talking about exact, down to the t, right? Now down to the last decimal. I want this thing to be accurate.
So it is always no, right? Even in real time data.
Yeah. So real world data, typically it is no. So I won't claim that I have a lot of experience with real world data, but usually you have a lot of data points and fewer vectors. So for example, I give you one example of a data set that you can go and look at, which is quite similar to what we have studied. So it's housing, the California housing prices. We will study this in MLT, machine learning techniques also. So if you look at the data, it's a CSV. Okay, so so these are the features, right? Longitude, latitude, total rooms, total bedrooms, population, right? So how many columns are there? Some 10 columns are there. Okay, so the number of rows, I don't know how to get the number of rows. Compact. Okay, so I don't know how to get the number of rows, but you can see, right, there are several rows here.
Yeah.
Right. So typically that's what will happen. You will have some small number of features, and several observations or data points. So you can fairly assume that You won't get an exact solution for this.
We can take this heuristically and say, see, our entire premise of machine learning is somehow it is solvable. That is our entire premise. And we will never know what is the exact solution, but somehow we want to find the closest solution. That is what our premise is.
Exactly. Yeah.
If it is mathematically solvable, we don't require it. This is all a heuristic explanation. If it's a mathematically solvable x theta equal to y, we don't require all this machine learning. We can use computers only, and somehow we'll find the solution.
True. Yeah.
So this is what heuristically why we are doing this is. That is what the explanation is. We will never be able to find the target function what is required.
Agreed. Yeah.
So we are finding somehow we are guessing what is the closest function which is possible. And if the target function does not exist at all, then there is no point of doing all this.
Right. Yeah. Agreed.
It is not mathematically sound the explanation, but heuristically it comes to that way only.
Yeah. So there is one quote which I have used here in the book, in the notes also it's there. So the quote goes like this: so all models are wrong, but some are useful. Right? So yeah, maybe if I don't tell that here, it would be wrong. So this linear regression is a model at the end of the day, right? It's not necessarily the best model, and it is wrong. Okay, so linear regression is wrong. In what sense? We don't know if the features are going to be linearly related to the output, right? As Srinivas mentioned, there is no necessity that selling price has to be a linear function of number of rooms, latitude, longitude, right? But no one has mandated that. We assume it so that we can at least do some sort of prediction and see if it can be useful, right? So useful is an important word. Accurate, exactly correct, right? 100% correct is not in the domain of ML.
One term is we should be satisfied with the word probably approximately correct.
Correct, yeah.
I think this word we should be satisfied with what is the answer given is probably approximately correct. We will never know what is the right answer, and that is not the objective, at least.
True. Okay, so any other questions? If not, we'll call it.
Sir, one question I have.
Yeah.
Sir, apart from mathematical ease, is there any reason why we choose squaring the difference in loss and not taking mod or any other?
Okay, so it's the function is convex. So you will study about convex functions. It becomes two things. It becomes easy to optimize. Taking the derivative of square root is troublesome, right? Painful. So that is one reason. The second reason is that one detail I missed. So you set the derivatives, the gradient to 0, but it could be maximum or minimum, right? I never told you which of these two it is. Second thing I didn't tell you is what if there are many minimas, right? Let's say there are 3-4 minimas. How do I know that this is a global minimum? So have you studied global minimum all that in Max 2?
Yes, it is.
You have studied, right? So yeah. So how do I know that this is the global minimum, right? It could as well be a local minimum. So when your function is convex, we will study this in week 7, 8, 9. Then if you differentiate and set it to 0, whatever solution you find will be the global minimum. There will be only global minimum. So there is a reason why we take this kind of loss. We square the loss.
Okay, thank you, sir.
Yeah. So any other questions?
Sir, in this week there was a topic Cauchy-Schwarz equation.
Right. Yeah.
So what is the use of it?
I also don't know, man. So I don't know where it is used. But if you want to know how it works, you must. So it's good to know Cauchy-Schwarz. Cauchy-Schwarz is a very popular inequality in mathematics. So
yeah,
it's useful to upper bound dot products. So if you are working with dot products x dot y, and if you want an upper bound for that, right? If you want to know, okay, roughly how much can it go? It can go only till norm x into norm y. If you
like for finding the maximum value of it.
Yeah. So if some kind of upper bounding, if you want, you can use that. If you want to know where it is used in ML, I also don't know. So if I find it, I will.
Mathematically, I also know, but not knowing that why it used in ML.
Correct. I don't know that. So
anyways, sir, it was a beautiful session. Thank you so much.
Yeah. So thanks everyone. I think if there are no other questions, we'll call it a day. Okay, then. So I think this week there are no more MLF sessions because of Paradox. We'll have to meet again next week.
Yeah, so you will come from next session?
I will be there for the next session on Monday.
Okay, sir. Thank you so much.
Okay. Thanks everyone.
Thank you, sir.
Yeah.